Hi, welcome back. I trust that you are enjoying your studies. Today we'll be looking at probability. So I have a compilation of questions here that are coming from the probability section of the syllabus. So let's look at the first question. The first question says, the probability that it will rain on any given day is X. He wears a hat is 0.3. Whether it is raining or not, if Aaron wears a hat, the probability that he wears a scarf is 0.4. If he does not wear a hat, the probability that he wears a scarf is 0.1. The probability that on a randomly chosen day, it is not raining and Aaron is not wearing a hat or a scarf is 0.3. Okay, so I have three situations here that I need to consider, but starting with whether or not it's raining. So I can do a tree diagram here. So I can say it's raining or raining complement, which means it's not raining. Okay, and if it's raining, he may or may not wear a hat. So I will have these branches for wearing a hat. When it's raining, he might wear a hat or might not wear a hat. If it's not raining, he might wear a hat or he might not wear a hat. If he's wearing a hat, he might wear a scarf or he might not. So scarf or no scarf. He might wear a scarf or might not. So these are the branches that I have. These are the branches of our tree, and then we have the same branch here. So the probability that he's not wearing a hat, so I will do this, and then S complement. Now let's fill in our probabilities. So the probability that it rains is X. Probabilities add up to 1. That means not raining is 1 minus X. If it's raining, the probability that he wears a hat is 0.8. That means the probability of not wearing a hat is 0.2. If he wears a hat, the probability that he wears a hat when it's raining is 0.3. The probability that he wears a hat, oh no, it says when it's not raining. Sorry, that's not where it's supposed to be. This is 0.3 for when it's not raining. So that means this is 0.7. Okay, it says whether it is raining or not, if Aaron wears a hat, the probability that he wears a scarf is 0.4. So on both occasions that he wears a hat, the probability of wearing a scarf is 0.4. So 0.4 here, 0.4 there. That means this will be 0.6. This here will be 0.6. If he does not wear a hat, then the probability that he wears a scarf is 0.1. So this is 0.1. This is then 0.9, and this is 0.1, and this is 0.9. Okay, so this is our tree. Now we can use the last statement there that says the probability that on a randomly chosen day, it is not raining, and Aaron is not wearing a hat, and he's not wearing a scarf. So not raining, not wearing a hat, not wearing a scarf, that is the last branch. So we are saying 1 minus X multiplied by 0.7 multiplied by 0.9 will be equal to 0.36. So that means then if I rearrange here, I have 1 minus X equal to 0.36, all this divided by 0.7 times 0.9. Okay, that means X will be equal to 3/7. Okay, we move on to the next question. It says Yuan goes to college each day by any one of car or by bus or walking. The probability that he goes by car is 0.2. So there are three possibilities. So I think a tree diagram will work here. So I'll say these are the three possibilities. So you might use a car, you might use a bus, or you might walk. The probability that he goes by car is 0.2. So I can write 0.2 here. The probability that he uses bus is 0.45. The probability that he walks to school, to college, is 0.35. So these probabilities must add up to 1. So if you add these, must add up to 1. When Yuan goes by car, the probability that he arrives early is 0.6. So if he goes by car, he might be early or not early. So early and early complement. The probability of being early is 0.6. That means not being early is 0.4. If then it says when he goes by bus, the probability that he arrives early is 0.1. So if he uses the bus, then the probability of being early and the probability of not being early, this one is 0.1. This one is, of course, then 0.9. So he's most probably going to be late if he uses the bus. Then it says when he walks, he's always early. Okay, so that means here, early or not early, that means there is no situation when he's late when he walks to school, to college, so he's always early. Okay, so this is our tree diagram. So it says draw a fully, we've just done that. Okay, that's good. All right, now it says find the probability that Juan goes to college by car, given that he arrives early. So there's a key word here that I see. It says given that. So this is conditional probability. So I must say probability of Juan going to college by car, given that he is early. Okay, so this will be the probability of using a car, intersection the probability of being early, divided by the given probability, which is the probability of being early. So I have to go to my tree diagram. The intersection of being early, using a car and being early is this branch that I've traced in green. So that is the probability. Okay, so that will be 0.6 multiplied by 0.2. Okay, so you simply plug in the values here, 0.2 times 0.6. And this is divided by the probability of being early. So let's look at the situations when he's early. The probability that is early will be obtained from these three branches. Okay, so what you want to do is you want to remember that when you're dealing with probabilities, when you use the word and, you multiply. When you use the word or, you add. So in other words, along the branches, you multiply. Between branches, you add. So for instance, if I say car, he uses the car and is early. Okay, car and early. Or it could be that he uses the bus and he is early. Or it could be that he walks and he is early. So you are multiplying the probability of using car multiplied by the probability of being early, then plus the probability of using a bus multiplied by the probability of being early, and so forth. Okay, so you just need to do that. So I am going to erase this. Okay, and I'll write down here the probabilities. Okay, so our denominator then becomes the probability of using a car and being early. And then I must add the probability of using the bus, which is 0.45, and being early multiplied by 0.1. So that is 0.45 times 0.1. And then plus the other probability, which is 0.35 times 1. So 0.35. Okay, so this gives me 24 over 103, which in decimal will be, this will be equal to 0.233. Okay, we are done with this one. Move on to the next. The next question says, two ordinary fair dice are red. One is red and the other is blue. They are thrown. Event A is that the score on the red die is divisible by 3. Event B is that the sum of the two scores, the scores on the two dice, is at least 9. Okay, so now I have, when you have two, so these are two experiments. You roll the first die, and you see what you get, and then you roll the second die and you see what you get. So I can use a sample space diagram here. So I can say rolling the red die and the blue die. It's red and blue die. Okay, I have outcomes, possible outcomes of 1, 2, 3, 4, 5, and 6. So these are my possible outcomes. And these are the same possible outcomes when you roll the red dice. So you have 1, 2, 3, 4, 5, and 6 when you roll the red die. So B requires that we get the sum of the two scores. So I'm going to write a plus here, okay, for sum of the scores. So that means in my space, sample space, I will have 2, 3, 4, 5, 6, 7. This will be 3, 4, 5, 6, 7, and 8. This will be 4, 5, 6, 7, 8, 9. This will be 5, 6, 7, 8, 9, and 10. This will be 6, 7, 8, 9, 10, 11. This will be 7, 8, 9, 10, 11, and 12. Okay, so this is our sample space diagram. Now we want to find the probability of A intersection B. So the probability of event A intersection event B. So that means event B is that the sum of the two scores must be at least 9. So that means I must draw a line here. So everything that is in this red triangle, or can I draw the triangle? Okay, so everything that's here, okay, let's just redraw this. Okay, so everything that's here describes event B, okay? These are possible outcomes for event B. And then the outcomes for event A is that we want the score on the red die to be divisible by 3, which means it's 3 and 6. So that means in our intersection with B, that will be 9, and that will be 9, 10, 11, and 12. So I have 1, 2, 3, 4, 5. So I have 5 out of the 36 possible outcomes. So my probability is 5 over 36. That is probability of A intersection B. Those are the two situations. Those are the situations where event A and event B will coincide. Hence, find whether or not the events are independent. Okay, so this is a test for independence. So we know that probability of A intersection B will be equal to the probability of A multiplied by the probability of B if the events are independent. Another way of saying this, which I'll just give here as a side thing note, is that the probability of A given B will be probability of A if the events are independent. That means that B occurring will not influence the probability of A. So the probability of A given B remains the probability of A. Okay, anyways, this is just a side thing. I'll erase that. We have already found the probability of A intersection B. So that means 5 over 6. So we have 5 over 36. So 5 over 36 must equal the probability of A times the probability of B. So what is the probability of A? A is that the score on the red die is divisible by 3. So that means the whole column corresponding to 3 and 6. So 1, 2, 3, 4, 5, 6 plus 6, that would be 12. So there are 12 situations when the score from the red die is divisible by 3. So this is going to be 12 over the total possible outcomes, which is 36. And then multiplied by B, which is everything that's in the red triangle, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which is 10 over 36. Okay, so if you put this in your calculator, you get 5 over 54. So then we can conclude that 5 over 36 is not equal to 5 over 54. Having said this, then it means that events A and B are not independent. So we can say, therefore, events A and B are not independent. Okay, so this question here says a total of 500 students were asked which one of 4 colleges they attended and whether they preferred soccer or hockey. The numbers of students in each category are shown in the following table. Okay, so you have the table here. Then they say find the probability that a randomly chosen student is at Kenton College and prefers hockey. So you have 500 students. So you are picking from n equal to 500. So there are 500 students. So the probability that they are coming from Kenton College and they prefer hockey will be 56 out of the 500. Okay, so where Kenton and hockey intersect, that would be 56. So you are going to say that would be 56 out of the 500. And if you simplify this, what do you get? What is 56 to 500? That gives me 14 over 125. Okay, we're done with this one. Then it says find the probability that a randomly chosen student is at Deva College, given that he prefers soccer. Okay, Deva College, given that. Okay, there's a keyword. The keyword is given that. So I'm going to say the probability that the student is at Deva College, given that they prefer soccer. This will be the probability of the student being at Deva and preferring soccer divided by the probability that they prefer soccer. Okay, so the probability of being at Deva and preferring soccer will be 120 out of the 500. We're still picking from 500. So this is going to be 120 out of 500. And we are going to divide that by the probability of preferring soccer. So preference for soccer is 280 out of 500. So this is 280 out of 500. Okay, so this simplifies to 120 over 500 multiplied by 500 over 280. So this is basically just 120 divided by 280. 120 divided by 280, which is 3 over 7. So this is 3 over 7. Okay. One of the students is chosen at random. Determine whether the student prefers hockey and the student is at Amos College or Ben College are independent, justifying your answer. So this is once again proving independence. So we can say the probability of the student preferring hockey intersection being from Amos College or being from Ben College. This must equal the probability of preferring hockey multiplied by the probability of being from Amos College or Ben College, right? So we can calculate these probabilities. So the probability of them being, so let me just calculate this probability. What is the probability that they prefer hockey intersection being from Amos College or Ben College? Okay, let's go back to our table and we should be able to pick this up. So Amos and Ben, so hockey preference is here and there, so out of the 500. So that's 72 plus 32 out of the 500. So here, this side, I have 72 plus 32 out of 500. And we want this to be equal to total hockey preference 220 out of the 500 multiplied by, remember we said earlier on, if you have probability of event A or event B happening, then you add the events. So I need the probability of A happening plus the probability of B happening. So let me just put a big bracket here. Probability of being from Amos College is 86 out of the 500. So this is going to be 86 out of the 500 students plus the probability of being from Ben College, which is 156 out of the 500. Okay, these are my probabilities. I want to see if they give me the same result on the left and the right hand side. So 72 plus 32, this gives me 72 plus 32 equal to 104. Okay, I left out a 0 here. So this is 104 over 500 equal to. And then I have 86 divided by 500. So this is what? 86 plus 156 equal to 242. 242 times 220 equal to, okay, this is equal to 5,324 divided by 500 times 500 is equal to 250,000. Okay. This simplifies to 53,240 divided by 150,000. This will be equal to 1331 over 6,250. Okay, so clearly this is not equal. Okay, so we can say that the events are not independent. Okay, therefore, not independent. Okay, not independent because they are not equal. Okay, so we are done with this one. So that's all you have to prove. Okay, so here it says for her bedtime drink, Suki has either chocolate, tea, or milk with probabilities of this. Okay, so this is again a tree diagram situation. I can just say this will happen. She will either have chocolate, she will have tea, or milk. Okay, the probabilities are respectively chocolate is 0.45, tea is 0.35, and then milk is 0.2. These probabilities must add up to 1. When she has chocolate, okay, the probability that she has a biscuit is 0.3. So she may or may not have a biscuit, so having a biscuit or not having it. Okay, when she has tea, okay, so let me just complete my tree diagram. So biscuit or no biscuit. Or she might have a biscuit or no biscuit. Okay, so let's fill in the probabilities. So the first one is 0.3, meaning this will be 0.7. Okay, if she has tea, the probability that she has a biscuit is 0.3 to 0.6, meaning this will be 0.4. Okay, when she has milk, she never has a biscuit. So this will be 0, this will be 1. Now find the probability that Suki has tea given that she does not have a biscuit. So that means this is a keyword given that. So I'm going to write probability that Suki has tea given that she does not have a biscuit, does not have. So that's biscuit complement, B complement. Okay, so this will be the probability of T intersection no biscuit divided by the probability of not having a biscuit. Okay, so this, of course, is going to be equal to the probability of T and no biscuit is going to be 0.35 multiplied by 0.4 divided by the probability of having no biscuit. So there are 3 situations, it's there, and there. So you multiply along the branch, you add between branches. Okay, so let me just multiply the values there, and that will be 0.45 times 0.7. So I have 0.45 times 0.7. That will give me a probability of 0.315. And here I have 0.35 times 0.4. That gives me a probability of 0.14. And of course, the other probability of not having a biscuit will be 0.2. Okay, so you want to multiply these numbers. So you are going to have 0.315. You add, you don't multiply. You add because it's between branches, 0.2. So this gives me 28 over 131. So this is the probability.